So I've been doing another experiment with string. I set up an apparatus. So we begin from here. It goes all the way down to there. Now watch this. So when you bounce this down, okay, wait, first let me talk to you about something. Newton's law. If you push something with a force going this way, then there'll be an equal force coming from this way. Same with this. If it goes down, then it goes up. So that's the same with this. It goes down and then it goes up, but then it continues. I'll get to that in a bit, how it continues. So first, when something goes up, you're acting against gravity. When you go up a hill, you're acting against gravity because you're going up. Now, since you're acting against gravity, this is called mechanical work. It's where the energy you use to go up the hill is dissipated and wasted into something called thermal energy, the energy of heat. But as you could see here, when it goes down, it will go up, but it would continue. And it continues many times. The reason why after it goes up, it continues, is because the energy can't escape the string that easily. But it can escape since it stops, as you can see there. Now we'll count the frequency of it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So it's about 20. So that's a lot as well. It's like when you throw a ball up. It goes there, and then it stops for the smallest time at the very top. It stops completely still, and then it goes faster at the bottom, because when it collides with the ground, it would start to go faster like that. So it starts like this, and then it bounces up, and then it bounces like that, and that, and that, and then that, until it completely stops, which is the same with this. It gets faster at the bottom, which is where the energy gets wasted. So energy cannot leave it completely, but as you can see, it has elastic potential energy because it's springy. Connie Springer, just joking. But if you concentrate your energy directly to the middle, then most of the energy will be concentrated to where you put the force to. It would be, let me draw the graph. It would be like that, and it would get closer towards the middle. I mean higher, the closer it gets to the middle. It would be like that. So does this mean there's more of a chance of it wasting energy at the top? No, because the more frequency there is, the more energy there is. And if you're good at mathematical probability, then you'll realize the more you have, the more chances of you finding something, I guess. Say there's a billion penguins and you're looking for one in particular. There's a very low chance that you wouldn't find it because there's so many of them. And it's like that. The more energy there is, the more chance of the energy leaving the system. But the question is, why is the energy so hard to leave? Does it depend on how you set up the apparatus? Well, no, because I tested that up already. So it doesn't depend on how much. No, actually it does, because if you get rid of this box, or you just do that, you wouldn't be able to spring it as well as you would do with the box. So this experiment shows us that the more it's pulled, the more you can spring it. In other words, the less elastic potential energy there is, the more elastic potential energy there is, the more energy will be concentrated if you were to hit it. Because as you can see, it's not being pulled. And when there's no elastic potential energy, it just wouldn't work, as you can see. But when it's being pulled, say I do this, see I do this, the more frequency there is. Obviously it will work better with the box on top of it. So this experiment shows us it needs to be pulled for it to for more so less elastic potential energy is needed for you to concentrate energy into the string, because when you just do that, the thing wouldn't work. So you need it to be pulled. As you can see, the more frequency there'll be. But can you tell if there's less elastic potential energy, or is there more elastic potential energy if it's pulled? Now that's what we're going to decide right now. If we pull it, is it still elastic? No, because you're using up all the elastic potential energy in pulling it. So when you concentrate gravity to this point, when you concentrate it, the energy wouldn't pull back the string from over here because there's no elastic potential energy in it. So there'll be less elastic potential energy in it. So we need to kick out the elastic potential energy, and that will change into thermal energy. We could call it thermal elastic, anti-elastic thermal energy, we could call it. So yeah, we need to kick that out, the elastic potential energy, and turn it into anti-elastic thermal energy for the energy to be concentrated. But okay, I'm gonna reset the apparatus now. I'm gonna reset it now. Right, now I'm going to reset it. Wait, do this. So now I'm going to put a string down, and then the box on top of the string. That's how you set this up if you want to explain this. So put this down. Okay, now it's done. So it's, as you can see, it's being pulled. But what happens to the string if we pull it over here? As you can see, the frequency isn't really concentrated that much over here. It's mostly concentrated to the rest of it, because because look, when you pull it down, there's not much force allowed. There's a limit as to there's a limit. You can't go down further than this point. So the less energy there is going down, the less energy there is going up to that point. But of course it has to move it needs to move, but not there. So the rest of it. But that means there's less energy being dissipated over here. There's less energy being dissipated because there's no elastic potential energy. In other words, it's not being able to be pulled, as we talked about anti-thermal elastic energy. That's pretty much it. And then apparently, according to according to famous scientists, if you do this experiment correctly, you summon a cat. And this cat was Schrodinger's cat. Yeah, you summon Schrodinger's cat. Now, if I point away, is the cat dead or is the cat alive? EM radiation, photons, electrons, protons, lithium.